Hello everyone, welcome to the third lecture of week 11 of the course Power Network Analysis. In this discussion, we will continue with our last module on the stability analysis of power networks, to be specific, transient rotor angle stability analysis of power network. And in this discussion, we will understand the premise of the equation or the numeric aspect of how transient rotor angle stability of a power network with several synchronous generators connected can be analyzed. And as the term transient rotor angle stability analysis mentions, by transient rotor angle, we are interested in the transients that are happening in the rotor angle of the synchronous generator, the rotor angle being the uh, on an assumption basis, the rotor angle being the angle of the internal EMF with respect to the terminal voltage of the synchronous generator. In case of a disturbance, how is that angle varying? What are the disturbances or repercussion effects on this angle? And whether the synchronous generator will remain in a stable operating condition following this disturbance. If at all it tends to remain in the same condition with respect to an initial equilibrium point, then how much have been the transient or variations? And if it is completely different from the previous initial operating condition, then what is that new operating condition in which the system tends to be in a stable condition? And obviously, when it is unstable, the rotor angle will tend to keep on increase or keep on decrease with respect to other synchronous generators in the power network, and eventually there will be a loss of synchronism, which in detail and length we have discussed in the previous lecture on basics and classification of power system stability problem, where we started with rotor angle stability, then understood about the small signal aspect, transient rotor angle aspect, voltage stability, frequency stability, and different forms of these classifications in different time domains under different disturbance size and the initial operating condition. So essentially the point that we all can conclude or understand that if the system tends to be stable, then the relevant variable, be it rotor angle, be it phase angle, be it voltage magnitude, frequency, they all tend to remain bounded and follow a particular trajectory. If the system tends to be in an unstable condition following a disturbance based on some initial operating condition, then also it is important to understand what this variable is likely to take its value, and can certain measures be taken into condition or taken into consideration that can minimize the impact of these unstable conditions. So today's discussion being on swing equation. Swing equation, let's see what that swing equation is. So before we go into the swing equation, which is the governing equation for transient rotor angle stability analysis as well as for small signal rotor angle stability analysis, we have discussed about the variations in a typical synchronous machine at length in the synchronous generator module as well as the previous module in fault analysis. If a disturbance happens, the disturbance could be a load change, line tripping, generation outage, excitation drop, and so on, or even occurrence of a fault, then the oscillations that appear in the rotor angle or the frequency or the rotor speed, the oscillations which occur or the transients that occur in these different variables pertaining to the synchronous machine or generator, they get some sort of a damping which is provided by the armature and the armature winding resistance, the network resistance, as well as the rotor damper windings. The notion of this damping comes into aspect of this. As a damper, it would tend to minimize the overshoots and undershoots that appear in these different variables, and resistance or network resistance happens to be a good damper in itself, which will tend to sort of minimize these variations. These rotor windings, they are usually shorted, specifically rotor damper windings, they are usually shorted by a large resistance which carry current only when the rotor speed differs from the synchronous speed. As long as rotor speed is same as synchronous speed, the rotor would never ever experience any slip or any variation in terms of induction machines, we call it to be slip, or associated frequency to be slip frequency. When the rotor speed is same as synchronous speed, we call the slip to be 0, and hence the damper windings which are present on the rotor, they don't have any induced EMF, as a result of which there is no current flowing in the corresponding rotor damper windings, as long as rotor speed is same as synchronous speed. If rotor speed is different from synchronous speed, then the rotor damper windings tend to carry a current at a frequency known as the slip frequency. For more details, please refer to the induction generator discussion in relevant textbooks and other chapters relevant, wherever you would find the relevant context. And the last part about synchronous machine parameters, specifically the reactance, is that it tends to vary after a disturbance, which leads to different time responses for a typical synchronous generator. And this response, as we have seen in length, can be divided into subtransient period, in which essentially we carry out the fault analysis study. The last part is the steady state period, in which usually we tend to carry out our power flow analysis. And essentially for power flow analysis, one doesn't need to go inside the machine terminal. Only the terminal information is sufficient enough, and hence usually the corresponding reactance or steady state synchronous reactance never ever comes into picture. The intermediate stage is the transient period, which lasts after the subtransient period before the steady state period and follows for certain few cycles, in which we would emphasize our current module or topic, which is transient rotor angle stability. And we would try to understand how these transients are happening, and corresponding transient reactance should be considered for analyzing this stability with respect to synchronous generators. So the purpose of transient rotor angle stability is to check that following a disturbance with respect to some initial operating condition, can the synchronous generator, be it motor or generator, can it remain in the conventional synchronized manner following a disturbance? There are 4 conditions for synchronism. Voltage magnitude should match with the terminal voltage of the incoming bus. Frequency should match, phase angles should match, and phase sequence should match. So this synchronism is mostly from the transient rotor angle stability perspective. It is more to do with the check that whether rotor speed is equal to the synchronous speed following a disturbance. If it is not, then how much is the deviation, and can the rotor speed again regain back its synchronous speed value? As I was mentioning also, that it is also a check whether the rotors of the machine return to their constant speed operation, which is the usual case following a disturbance. If there has been a deviation in the rotor speed, then how much has been the deviation, and can something be done to bring back the rotor speed to the actual synchronous speed, so that the conditions of synchronism are well satisfied and well maintained. So in order to do this analysis or understand this transient rotor angle stability or instability analysis, obviously any analysis or study goes by with some assumptions. I'll just explain those assumptions, and I would call them to be the assumptions associated with the conventional transient rotor angle stability analysis. The assumptions do have some basis, but it is not necessary that from the practical network perspective these assumptions should always hold true. In case these assumptions don't hold true and one has to go beyond the conventional transient rotor angle stability analysis, then appropriate considerations have to be considered. So in conventional transient rotor angle stability analysis, we will not consider the dynamics or changes that are happening in the automatic load frequency control, ALFC, or the automatic generation control effect, which in a way tends to regulate the mechanical input of a synchronous generator given the load change, increase or decrease. And as a result, since those dynamics of ALFC or the corresponding turbine control, they are much slower compared to the transient period in which we would be interested in understanding the rotor angle stability or instability aspect. So we would consider those dynamics to be not present or not to be considered. And hence the bottom line is that the mechanical input of a synchronous machine In a generator, it is the input. In case of a motor, it is the output. It would always remain constant. The machine and system damping and the voltage regulation effects are also neglected, again from the conventional perspective, but from practice or practical perspective, this may not be applicable. And the synchronous machine or generator is represented by a constant internal EMF similar to fault analysis module in series with a direct axis transient reactance. In fault analysis, we had the direct axis subtransient reactance, which was XD double dash. For transient rotor angle stability, we will focus on using the direct axis transient reactance, because the direct axis transient reactance is the dominant reactance. The corresponding quadrature axis reactances are negligible. On similar lines, network transients are also to be neglected, that is transmission line resistance, the corresponding load damping, load modeling or load effect on load sensitivity towards voltage, load sensitivity towards frequency, which we will discuss a bit towards the end of this particular module. And we had also talked about these different load models when we discussed the load power flow analysis module. So, we'll briefly touch upon those practical models which tend to bring in deviation from the conventional transient rotor angle stability analysis. For conventional sake, network transients are neglected. Line is modeled by a static lumped pi model. The entire network is reduced only to the machine nodes. By machine nodes, I mean buses or nodes which are directly connected to the internal EMFs of the synchronous generator. These internal EMFs refer to the constant internal EMF, which I was referring to in the previous slide. And we will make use of a special technique known as ward reduction, which is also a generalized or a specific form of Cron reduction, which we will talk at length in a particular lecture to come up. And the benefit of all these assumptions is that one need not do extensive power flow analysis. And why power flow, one would wonder why it is needed. The purpose remains the same. When we did fault analysis, we have to have an estimate of what was our initial pre-fault voltage. For any stability problem, we have to also understand what is our initial equilibrium point or initial steady state operating condition. And without doing power flow or state estimation, we won't be able to get those estimates. One practically should do power flow to get these initial operating conditions, but then from conventional perspective, one can make use of ward reduction with some assumptions on these internal EMFs to make the process faster and avoid power flow entirely. Load dynamics are, as I mentioned, they are neglected and they are all modeled as constant impedance or admittance type model. No load dependency on voltage or frequency is considered, which should be considered otherwise practically. And the biggest assumption, as I mentioned in the initial few slides of this lecture, is that the machine's internal EMF angle, it coincides with the machine's rotor angle. By internal EMF angle, I specifically mean the angle of internal EMF EF, which is, let's say, at an angle delta, measured with respect to the terminal voltage of the synchronous generator, which we are choosing as zero reference for phasor measurement. Now, this angle delta, it is usually positive, or it should be positive for generating action, and it is negative for motor action. By rotor angle, we are assuming that this delta angle itself pertains to machine's rotor angle, and it is a direct measure of that particular angle deviation which we are trying to measure at. The rotor saliency aspects are neglected. We would be consistently considering the cylindrical machine-based rotor or cylindrical pole rotor for our discussion, although from practical perspective, some countermeasures have to be considered to do this transient rotor angle stability analysis for salient pole machines. And in general, we would be using some static power flow equations. In general, some power flow based equations, I won't say the usual power flow equations, but some power based equations for representing the reduced network which we obtained by ward reduction, and certain second order differential equations which are dynamic equations representing the rotor variation or rotation, which together we would be using for understanding this module of interest. So, essentially we will be dealing with some differential equations, also with, in addition to some static power based relationships between power and the phase angles. So coming to the swing equation, which is basically defining or governing equation behind the rotor dynamics of a synchronous machine during a disturbance, that swing equation, it is a second order differential equation of this form. Before I go deep into what this swing equation means, let us try to revisit or recollect what is our Newton's second law of motion. Newton's second law of motion. Newton's second law of motion is mathematically represented by an equation of the form mass into d square x by dt square, where x is distance or displacement, t is time. It is equal to some force. Now here m is mass, as I mentioned. Double derivative of distance or displacement with respect to time is acceleration, and F is the net force which is acting on this mass m. Now, the second law of motion, what it indicates, what it represents, it represents that if some force is applied or some non-zero force is applied on a mass m, which may be stationary or non-stationary before the force was applied, it will eventually experience an acceleration which would tend to increase its distance or displacement and corresponding speed or velocity. If the same set of analogy is to be applied on the rotors of our synchronous machines, then since the rotor is a rotating body and has some kinetic energy, some mass associated with it, it is not a massless body. So in case the rotor tends to experience some sort of a torque or force in rotating medium, then the corresponding dynamics which would be observed in the rotor angle, which is basically theta m, is indicated by this similar Newton's second law of motion analogous equation, which we call as swing equation from power network perspective. So in this equation, swing equation, J refers to total moment of inertia of rotor and combined together in kg meter square. Theta m is the absolute rotor angle displacement with respect to a stationary axis on the generator stator measured in mechanical radians. T is time, small t is time here, as I mentioned. Tm is the mechanical input torque or shaft torque supplied by the prime mover with negligible losses considered. So its unit is Newton meter, which if applied tends to bring in a positive effect on the torque, and it tends to accelerate the rotor with theta m increasing in time. Te is the counter electromagnetic torque which is produced because machine is delivering electrical power output, and because of armature reaction effect, the stator also tends to get a pushback that, oh, let's not only accelerate, let's also bring in a counterbalance between mechanical input and electrical output. So that corresponding counter torque is known as the electromagnetic torque, which comes in because of power output, electrical power output of the synchronous generator, which tends to deaccelerate the rotor if T is non-zero, and hence in a way it is accelerating rotor in the negative theta m. And Ta is the net acceleration torque, which is in Newton meter. Now under steady state, as I mentioned, as long as there is a balance between the mechanical input to the generator and electrical output of the generator, considering negligible losses for the sake of simplicity in our discussion, then Ta under steady state would be perfectly zero, which would mean that this entire terms becomes zero, which means the rotor is not experiencing any acceleration or deacceleration under steady state condition. And as a result, during steady state, which is the usual case, rotor speed is the same as the constant synchronous speed, and rotor and turbine, they are happily together in synchronism with no variations in the rotor speed or the corresponding rotor angle. Now, in terms of mechanical torque or the shaft torque, since we are neglecting the effect of AGC control, turbine control, because their dynamics are smaller or their dynamic inertial time constant is smaller. So for our study of transient rotor angle stability analysis, we would consider Tm to be constant. However, the electromagnetic torque Te, it can change because of the disturbance which is occurring in the generator electrically from the transient rotor angle stability perspective, and hence the corresponding changes which can happen for transient rotor angle stability, they would all happen for the electrical power output or the electromagnetic torque perspective, which in a way accounts for power transfer between the rotor to the stator through the air gap. Now, if we talk about our angle theta m, which is being measured with respect to a stationary axis on the stator. So let's focus on the steady state condition to be a precise case. So in steady state condition, what we observe that uh, since acceleration torque is 0, so d square theta m by dt square would be 0, because j cannot be 0. It is referring to moment of inertia of a physical device, so j cannot be 0, and hence the rotor acceleration is effectively 0, which would mean that if I integrate with respect to some initial condition, then d theta m by dt is basically a constant c, and which if I further integrate, then theta m is some c of t plus k, where c and k are integration constants depending on some time condition. So which would mean that even when the rotor is not experiencing any acceleration or deceleration, that is perfectly zero in steady state, theta m on the other hand is continuously varying with time. And mathematically speaking, it looks all okay, but from a power network or an engineer perspective, we are actually interested, from the transient rotor angle stability perspective, we are actually interested in understanding the third aspect, which says if rotor speed has deviated, how much has been the deviation. We are not actually interested in the absolute change in the rotor angle with respect to some stationary axis. So can something be done for easier analysis with the swing equation understanding remain intact? Yes. What we can do is, as I mentioned, we are interested in the rotor speed with respect to synchronous speed and not the actual rotor speed to be in a practical essence perspective, because we know for sure that the system is stable and the rotor speed would be same as the synchronous speed. So what we can do is we can change the reference with which this rotor angle theta m is being measured. Instead of measuring it with respect to some stationary axis on the stator, can we not measure it with respect to some rotating axis, again with respect to stator, and the rotating axis coincidentally can happen to be the rotating stator flux in the air gap of a synchronous generator, which rotates at synchronous speed under steady state conditions. So what we are interested is, as I mentioned, we are interested in measuring the rotor angle position with respect to a reference axis, which is also rotating at the synchronous speed, and that can happen to be the rotor, not the rotor, because rotor is undergoing dynamics. This reference axis can be the stator air gap flux, which is rotating in the air gap at a synchronous speed. So what we are doing is we are trying to change the reference for theta m, and the associated terms that come in are omega sm, where omega sm is the synchronous speed of machine measured with respect to the same stationary axis of stator, which based on which theta m was being measured. T is the time, and delta m now happens to be our analogous rotor angle, which is being measured with respect to the synchronous rotating reference axis. So with this change in our reference point, because now any deviation which is happening between this synchronous rotating reference axis and the stationary axis, it is getting compensated through this omega sm angular speed. So delta m can happen to be our new analogous transient rotor angle, which will help us in getting the analysis of rotor speed with respect to synchronous speed. So what we do is we try to find the first and second derivative of theta m, so that we can get the corresponding expressions in terms of delta m. And when we take the first derivative of theta m, which is nothing but omega m, now omega m is the actual rotor speed measured with respect to the same stationary axis with which omega sm is being measured and theta m is being measured. So the corresponding first derivative is omega sm plus the first derivative of delta m, and the second derivatives, they are perfectly identical to each other, because omega sm happens to be a time independent quantity. Now what is the situation when things are in steady state? When things are in steady state, we know for sure that these two terms would be equal to 0, if these two terms are equal to 0, then it also means that d delta m by dt would also be 0, and that is where omega m is equal to omega sm when the relative motion between rotor and synchronous rotating reference speed is 0, which means that under steady state, when the rotor speed is same as the synchronous speed of the motor, omega sm, which is basically the synchronous speed of machine, and omega m, which is the rotor speed of machine, both being measured on the same reference axis, in steady state rotor speed would be same as the synchronous speed. So omega m has to be same as omega sm, and under that condition, when there is no deviation, d delta m by dt would also be 0. And in case there is any disturbance or deviation which brings in a change of this expression not being equal to 0, under that condition d delta m by dt would also be not equal to 0. So essentially, the swing equation which was defined in terms of theta m can be rewritten in terms of delta m, and often as electrical engineers it is convenient for us to deal with power rather than torque. So we can also multiply both the sides with omega m, which is the actual rotor speed with respect to some stationary axis on the stator. So the corresponding torque into speed is nothing but electrical power, which is in watts. So this becomes our analogous swing equation, which we can use further for analyzing the transient rotor angle stability of synchronous generators. Pm now becomes the input turbine power, mechanical input power to the generator. P is the electrical power output crossing the air gap in watts. J omega m is the angular momentum of the rotor and the turbine considered together. And we also define another term or constant known as capital M, which is j omega sm and not j omega m. Omega sm, as defined on slide number 8, is the synchronous speed of the machine measured with respect to a stationary axis. And for a machine which is already designed and operational, synchronous speed being function of frequency and number of poles in steady state. Under steady state, frequency won't change, number of poles in the machine won't change. So omega sm is actually a constant for a given machine, and hence capital M is also a unique constant for every synchronous generator, because J is again the moment of inertia of a physical device, rotor and turbine combined together. Omega sm is a fixed quantity for a given generator. So capital M is the inertia constant of machine angular momentum of rotor and turbine considered together in kg meter square radian per second. So what we do for, again, the sake of simplicity, is we tend to replace j omega m in the equation shown over here by capital M, and hence this becomes our analogous swing equation, which we will discuss further in the next lecture. It is true that capital M is not the actual angular momentum of rotor, and there might be deviations or variations in transient rotor angle stability analysis results, but inertia constant m actually not being a constant doesn't make much of a deviation. This sort of a assumption, it tends to go well with transient rotor angle stability analysis. So that's all for today's discussion. In the next lecture, we will continue with our discussion on swing equation, in which we will at length talk about how this equation can be analyzed under different disturbances, and what can be done, or what sort of stability or instability problems that might come up under different disturbances through use of this equation, that we will discuss in the next lecture. Thank you.